So we will see that for if your abstract transfer functions satisfy a more stronger property, right, which is distributivity, then LFP of f bar will be equal to the abstract GOP, right. So for that, let's first define this notion of distributivity, right. So what are distributive and infinitely distributive functions? Okay. So this is the so we'll go back to lattice theory, right. So this is the lattice theoretic definition of a distributive function, right. So if you have two posets d1 and d2 and this function f from d1 to d2, then we say that this function f is distributive um, if you take any two elements x and y of d1 and such that their join exists, right. So remember, this is just a poset, right. So the join may or may not exist, right. So but if x join y exists in the lattice d1, then this fx join fy lattice fx join fy in the lattice d2, or rather in the poset d2, this join is also guaranteed to exist. And not only that, but this f of x join y will be equal to f of x join with f of y, right. So which means that essentially you either take the join in d1 and then apply the function f. This is the same as first applying the function f and then taking the join in the lattice d2. Okay, so this f essentially distributes over the join. So if that is the case, then f is called distributive. So f is called infinitely distributive if instead of taking just two elements, right, you can take any arbitrary subset x of d1, right. So if you take any arbitrary subset x, right, consisting of any number of elements such that the join of this set exists, right, then if you take the image, right, which is f of x, its join also exists. And not only that, but the join is also going as a the f is again going to distribute over this join, right, which means that this f applied over the join of x is going to be equal to taking the image f of x and then the join in the lattice d2. Okay. So as an exercise, right, you can try to show that if f is distributive, then f is also monotonic, right. So distributivity implies monotonicity. Okay. So how do we show this, right? So let's assume that f is distributive and we want to show that f is monotonic. So to show that f is monotonic, we have to essentially take, right, two elements, right. Let's say we take these elements d1 and d1 prime. So let's take two elements d1 and d1 prime such that they are in the lattice d1, and you have d1 is less than or equal to d1 prime. So this is in the lattice d1, right. So less than or equal to 1. So now you have to show, right, so we have to prove that this f of d1 is going to be less than or equal to f of d1 prime, but this is in the lattice 2, right. So you take less than or equal to 2 relation. So this is what we need to show that f is monotonic, but we know that f is distributive, right. Okay, so if d1 is less than or equal to d1 prime, okay, so what can you say about the join, right, of d1 and d1 prime in the lattice 1? So we have seen earlier, right, that if d1 is less than or equal to d1 prime, then the least upper bound of d1 and d1 prime, this is nothing but d1 prime itself, right. So f of d1 joined with d1 prime is equal to d1 joined with d1 prime is equal to d1 prime. So this is a property of the least upper bound, right. This has nothing to do with the function f, right, because d1 prime is going to be the least upper bound of d1 and d1 prime, right, if d1 is less than or equal to d1 prime. Okay. So now let me apply the function f on both directions, right. So now I have f of d1 join 1 with d1 prime, this is equal to f of d1 prime. Okay. But now let me use the fact that the function is distributive, right. So the function is distributive. So therefore this f of d1 join 1 d1 prime, this is the same as f of d1 joined with f of join, but in the lattice d2 with f of d1 prime. So essentially the f distributes over the join, right. So f of d1 joined with f of d1 prime, this is now equal to f of d1 prime. Okay. So now what is this saying, right? So this is saying that the least upper bound of these two elements, right, but in the lattice d2, this is equal to f of d1 prime. This can only happen, right. So remember, they have f of d1 and have f of d1 prime, their least upper bound is equal to f of d1 prime, right. So since f of d1 prime is a least upper bound, it's also an upper bound of both of these elements, right? So therefore, since right f of d1 prime is an upper bound of f of d1, right, you will get f of sorry, let me write this here. So you'll get f of d1 less than or equal to f of d1 prime, which is what we wanted to prove, right? That f of d1 is less than or equal to f of d1 prime. So this shows that if f is distributive, then it's also monotonic, right? So similarly, you can also show that if f is infinitely distributive, it's obviously also distributive, and therefore it's also monotonic. Okay. So as I said, right, the goal behind introducing this notion of infinitely distributive, right, is that we want to see, right, when this abstract GOP will be equal to the LFP of f bar, right? So now we will show that if you have an infinitely distributive abstract interpretation framework, which means that every abstract transfer function is infinitely distributive, then in fact the abstract GOP will be equal to the LFP of f bar, right? So this is the meaning of an infinitely distributive abstract interpretation framework, right, which is that all the functions, right, all the abstract transfer functions, they are infinitely distributive, right? So if all the abstract transfer functions are infinitely distributive, then the abstract GOP is equal to LFP of f bar, okay? And this is what we will prove. So the way we will show this, right, is we are going to show that this abstract GOP is going to be a fixed point of the function f bar itself, right? And this is sufficient to prove the result. Okay. So why is that the case? So let's try to untangle this, right? So what do we know, right? So we know that if, right, so if let's say this AI, right, this abstract interpretation framework D is infinitely distributive, then I also know that this abstract interpretation framework is monotonic. Why is that? Because we have already seen, right, that if a function is infinitely distributive, it's also distributive, and therefore it's also monotonic, right? So which means that all the abstract transfer functions are also going to be monotonic, which means that the abstract interpretation framework itself is going to be monotonic. So if the framework is monotonic, we have already shown this, right, that if you have an monotonic abstract interpretation framework, then the abstract GOP is less than or equal to LFP of f bar. So this we have already shown, right? So which means that if your abstract interpretation framework is infinitely distributive, then also the abstract GOP is less than or equal to LFP of f bar. Okay. Now if you also show in addition, right, that this abstract GOP, which is mu hat, is a fixed point of the function f bar, right? If it is a fixed point of the function f bar, remember that LFP of f bar is the least fixed point of f bar, right? So that would mean that the LFP of f bar, right, will also be less than or equal to abstract GOP. So if you are able to show that the abstract GOP is a fixed point of the function f bar, so now we have both directions, right? So abstract GOP less than or equal to LFP of f bar, and LFP of f bar less than or equal to abstract GOP. So this will mean that the abstract GOP is equal to the LFP of f bar. Okay. So therefore our goal now is to simply show that this abstract GOP is a fixed point of f bar. Okay. Okay. So how do we show this? So let us try to expand, right, what is this abstract GOP. In particular, right, what we are going to do is we are essentially going to apply, right, this f bar on mu hat. So remember f bar, right, see f bar is a function on the vectorized lattice, right? So it is from d bar to d bar. So I'm kind of reinterpreting, right, this abstract GOP mu hat also as a vector, right? So mu hat earlier we said is a function, right, from L to D, but I can also view this mu hat as a vector, right? Essentially this vector mu hat of L0, mu hat of L1, and so on, right, up to mu hat of L, right? So by that logic, mu hat is also so this mu hat, right, this is also a member of the vectorized lattice. So mu hat is a member of D bar. So therefore I can apply f bar on this mu hat, right? And let me do that, right? So here I have applied f bar on mu hat by treating this mu hat as a vector, and in particular I am interested in the value of this resultant vector, right? So f bar is a function from d bar to d bar. So it takes this input, a vector gives another vector. So I'm looking at the lth component of that vector, right? Essentially I'm looking at the component of that vector corresponding to the location L, right? And this again we have defined, right? So this f bar, right, at the location L, right? This we have defined earlier to be f bar at the location L of some vector d bar, right? So sorry, so I should write it properly. So f bar applied over d bar, this is a vector at the location L. This is defined to be this join, right, of this f hat c. If you take, for taking every predecessor, right, L prime c L belongs to T, f bar c of d bar at L prime. So this is how we have defined the function f bar. Okay. So all I'm using, I'm just using this definition, right? But instead of having d bar, I have mu hat, right? So this is what is happening here, right? So f bar of mu hat at the location L, this is nothing but taking all the predecessors, right, of the location L. So L prime is a predecessor of the location L, and then applying f hat p of mu hat of L prime, right? So this d bar is taken to be mu hat. Okay. So now let me expand this mu hat, right? So mu hat of L prime, this is the abstract GOP at the location L prime, right? So what that means is you take every possible path to the location L prime, and then along all those paths you compute the abstract values and then take their join, right? So all I have done is I have just expanded that mu hat of L prime, right? So taking all paths pi to the location L prime and then computing the abstract values reachable along those paths and then taking their join. Okay, so this is what is the definition of mu hat of L prime. Now here is where I use the fact that this f bar p, right, this remember is the abstract transfer function of the program command p. So this is distributive, right? This is in fact infinitely distributive because all abstract transfer functions are infinitely distributive, right? So here instead of applying the function f bar over a join, right, since this f bar p, it's infinitely distributive, it's going to distribute over the join, right? So I can instead take the join of by first applying the function and then taking the join, right? So this is what I have done, right? So I'm just taking this f bar inside, which I can do because f bar p is infinitely distributive, right? So now I have this join, this inner join has come outside, right? So the join over all location or all paths pi to the location L prime, and this f bar p has gone inside, right? So I have f bar p of f hat f hat p of f hat pi of d0. Okay. So now let us look at this carefully, right? So what is this? Okay. So in particular, right, I mean, if you take this location L, right, this location L, let's say it has a bunch of predecessors, okay, one of which is this particular predecessor L prime, right. So what you are really doing is that you are taking each of these predecessors and then you are taking all paths to that predecessor from the start location L0, right, and you are doing this for each of the predecessors, right. So for each of these predecessors, right, you take the path to that predecessor and then you apply the abstract transfer function corresponding to the edge, right, for that predecessor. So this f hat p is applied over the abstract value which is reachable at the end of each of the paths to the location L prime, and you do this for each of the predecessors L prime, right. So this is nothing but essentially computing the abstract values, right, that are reachable at the location L through any of the paths from the start location L0, right. So from the start location L0, if you take any path to the location L, it is going to pass through one of the predecessors, right, and the abstract value along that path is going to be present, right, in one of these joins. Okay. So because of the fact that join is associative, right, which means that it doesn't matter the order in which you take the join, right, what this is essentially computing is the same as the abstract GOP, right, which is this mu hat at the location L. So mu hat at the location L is nothing but the join over all paths to the location L from the start location, right, but all of those paths will be now encapsulated, right, through one of its predecessors L prime, right. So any path to location L is going to come through one of the predecessors L prime, and the abstract value reachable along that path is already part of this particular computation, right. So therefore, due to associativity, we get the fact that this f bar of mu hat of L, this is the same as mu hat of L. So this is exactly what we wanted to show, right. So in order to show that this mu hat is a fixed point of the function f bar, right, you have to show that f bar of mu hat is the same as mu hat, right, which means for all locations L, you have to show that f bar of mu hat at the location L, this is the same as mu hat at the location L, and this is exactly what we have shown, right. So this means that mu hat is a fixed point of f bar, and so we already know, right, that so this means that since LFP of f bar is the least fixed point of f bar and mu hat is a fixed point, therefore mu hat is less than or equal to LFP of f bar, and earlier results, right, have already shown that LFP of f bar is less than or equal to mu hat. This we have shown separately for a monotonic AI framework, right, but every infinitely distributed AI framework is also monotonic. So this means that mu hat will be equal to LFP of f bar, right. So therefore, for an infinitely distributive AI framework, computing the least fixed point of f bar is the same as computing the abstract GOP. So recall, right, so in the sign abstract domain, right, in particular we had an example, right, where the LFP of f bar was not equal to the abstract GOP, right. In fact, the reason why this is happening is because the abstract transfer functions of the sign abstract domain, they are monotonic, but they are not infinitely distributive, right. So in particular, they are not even distributive. So since the abstract transfer functions are not distributive, therefore the LFP of f bar is not equal to the abstract GOP. Okay. So in particular, right, if you just take this particular program statement, right, which is j equal to I into k, okay, and this, remember, this was one of the program statements, right, in the problematic program, right, that we had seen earlier, where the abstract GOP was not equal to the LFP of f bar. So if you take this particular program statement P, let's try to compute, right, what will be f hat of P, right, which is the abstract transfer function of this particular program called P, right. So in particular, we will show that this f hat of P, this is not distributive. Okay. And the way we will show it is, we will show it through a counter example, right. So let's consider these two abstract values d1 and d2, right. So this d1 and d2 are two abstract values in the sign abstract domain. Remember, there are three variables I, j and k, right. So these are the signs of the three variables, right. So this is I, this is sign of j, and this is sign of k. Okay. So let's take d1 to be this plus, plus, minus and plus, and d2 to be minus, plus, minus and plus, minus, plus, minus and minus rather. Okay. So let's try to compute this f hat P of d1 join d2. So what's going to be f hat P of d1 join d2? So in particular, what is d1 join d2? So in the vectorized lattice, right, join is pointwise, which means that you just take the join of the corresponding points, right. So plus join with minus will give you plus minus, plus minus join with plus minus will give you plus minus, and similarly plus join with minus will also give you plus minus. So this is d1 join d2. So what is f hat P of plus minus, plus minus and plus minus? Okay. So in particular, right, what is the effect of executing this program command on the states which are encapsulated by this abstract domain, right. So here I know that I, j and k can take any values. Since so I'm changing the value of j, right. So the value of I and k will remain as it is, right. So for I and k, the value will remain as it is. What will be the new value for j? So j is obtained by multiplying I and k, but since I can be positive or negative and k can also be positive or negative, therefore I cannot guarantee, right, whether j will be positive or negative, right. So it will, in fact, it can be either. So therefore f hat P of plus minus, plus minus, plus minus will be equal to plus minus, plus minus and plus minus. Okay. But now something interesting happens, right. So let's try to compute this f hat P of d1 joined with f hat P of d2. So in particular, what is going to be f hat P of plus, plus minus and plus? Okay. So again, right, this is not going to change the value of I and k, right. So the value of I and k will remain plus. What about the value of j, right? So the value of j is going to change now. So its original value doesn't matter. So it's obtained by multiplying I and k, but I know that I and k are both positive. So if you multiply two positive numbers, you get a positive number. You are guaranteed to get a positive number, right? So therefore, the value of j after executing this program statement is guaranteed to be positive, right? Therefore, the abstract value will also be plus. Similarly, let's compute f hat p of d2, right, which is minus, plus, minus and minus. Okay. So again, right, the value of I and k will remain the same. What about the value of j? Right. So again, you are multiplying two numbers I and k, but they are both negative here. If you multiply two negative numbers, you are guaranteed to get a positive number, right, no matter what the negative numbers are. So therefore, after performing this computation, right, if I and k are guaranteed to be negative, then j is guaranteed to be positive, right. So now you take their join. So again, you take the pointwise join. So you will get plus minus, plus and plus minus, right. So therefore, this will be plus minus, plus 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 join with minus minus plus minus, which is the same as plus minus plus and plus minus, right. So therefore, this shows, right, that this f hat p of d1 joined d2 is not the same as f hat p of d1 joined with f hat p of d2, right. So therefore, this f hat p in fact doesn't distribute over the join, right. So therefore, this is not an infinitely distributive framework, and this is the reason why for the sign abstract domain, right, if you apply Kildall's algorithm, right, the LFP of f bar that is computed is not equal to the abstract GOP. Right? In fact, it over approximates the abstract GOP. So another interesting observation, right, is that the concrete transfer functions, right, which is this FP, right. So remember, this FP are the set of concrete transfer functions which are from the power set of states to the power set of states. Right? So they are on the over the concrete lattice. Right? So these concrete transfer functions are always guaranteed to be infinitely distributive. Again, you can try to separately prove this, right, that the concrete transfer functions are always going to be infinitely distributive. Since they are always going to be infinitely distributive, therefore, if you take LFP of f bar, but where this f bar is composed of the concrete transfer functions, right, then you get the concrete GOP, and this concrete, in fact, you will get the least fixed point of the concrete data flow equations, and since the concrete transfer functions are always infinitely distributive, therefore you will actually get the concrete GOP, right. So in fact, this is the reason why the forward propagate algorithm, right. So this is one of the very first algorithms that we saw when we started this module, right. So the forward propagate algorithm, which is nothing but Kildall's algorithm, but with the concrete transfer functions, right. This is guaranteed to compute the concrete join over paths, right, which is nothing but the exact set of reachable program states at every program location. Right? So the concrete so the Kildall's algorithm applied over the concrete program, over the concrete set of program states, right, doesn't introduce any over approximation, right. So it's only when you have a function which is not distributive that you get over approximation. Okay. So let us try to kind of summarize everything that we have seen, right, through this big picture. Okay. So on the left hand side, I have my concrete. So this is my concrete program. This is the concrete domain, right, which is the set of concrete program states, right. So every element of this concrete domain is a set of program states, right, it's a set of valuations of program variables. So this is what we call the power set lattice, right, it's guaranteed to be a complete lattice and so on. Okay. On the right hand side, I have my abstract domain, right, and as we have seen, right, this abstract domain has to be a complete lattice, right, and Galois connection with concrete domain and so on, okay, along with consistent abstractions. Okay. So this is what I want to compute, right, for every location L, I want to compute the concrete GOP, right, which is the set of concrete program states which are reachable at that location L. But this I cannot compute because forward propagate doesn't always terminate, right. So instead I compute this mu hat of L, right, or this is again what I want to compute, right, which is abstract GOP, right. So this is the abstract join over paths, and as we saw earlier, right, that under some conditions, right, namely that this abstract domain being a complete lattice, right, the abstract transfer functions being consistent abstractions and so on, this mu hat of L over approximates mu of L, right, which means that if you take the concretization of mu hat of L, this gamma of mu hat of L is guaranteed to be a superset of mu of L, right. So therefore you can use this mu hat of L soundly. Now as we have seen in this lecture, right, that Kildall's algorithm actually doesn't compute this mu hat of L, but instead it computes something else, right, which is this LFP of f bar, which is another element in the abstract domain, right. And and this is only under the constraint that your abstract interpretation framework is monotonic, right, which means all the abstract transfer functions are monotonic. So under this assumption, right, where the AI framework is monotonic, we have seen, right, in today's lecture that mu hat of L is less than or equal to LFP of f bar. Okay. which means that LFP of f bar always over approximates the abstract GOP. And again, right, what this means is, since gamma is monotonic, right, therefore if you take its gamma image, this gamma of LFP of f bar again is going to be another over approximation of this gamma of mu hat of L, right, which in turn is an over approximation of mu of L. Right? So again, all this means is you can safely use this LFP of f bar, right. So using LFP of f bar is sound. Okay. So this is for a monotonic framework, but if your abstract interpretation framework is infinitely distributive, then in fact this LFP of f bar is actually equal to the abstract GOP, and therefore we know that again, right, since the abstract GOP also over approximates the concrete GOP, you can again soundly use LFP of f bar. Okay. So it doesn't introduce any over approximation, but this is only if your abstract interpretation framework is infinitely distributive. Okay. So now the only thing that is remaining, right, is to show that Kildall's algorithm actually computes this LFP of f bar. Okay. So that will show in the next lecture. So let's finish the lecture today. Thank you.